So today we're very happy to have Xiao-Gang Wen from MIT. He will be telling us about, well, you can see the title and the transparencies, symmetry and algebraic symmetry as a shadow topological order. And we're experiencing today one of the benefits of remote seminars, which is that we didn't get snowed out today. And we're probably all or almost all comfortably in warm places at home, probably. So anyway, Xiao-Gang, please go ahead.
Okay, yeah, I'd like to thank Edward for to invite me to give this chance to talk about some of our recent work. And yeah, today is snowing in Princeton. Also, we are snowing in Boston. But usually, I really enjoy my visit to IAS. You know, I remember the pond, the grass. It's such a wonderful environment. And hope later we'll have a chance. Just not giving seminar virtually.
Yes, hopefully next time we'll be in person.
So today I'm going to talk about some kind of a categorical or holographic view of symmetry. So at the beginning, we'll discuss symmetry and also introduce algebraic symmetry using some simple examples. And then we'll try to formulate some general theory of those symmetry. There's two general theory, one in terms of a fusion higher category, another is in terms of a topological order in one higher dimension. But first, let me just discuss some simple examples. So we consider a bosonic lattice model, and where each side have a degree freedom labeled by the group element. So the symmetry act from the right, for example, and then under this kind of symmetry action of a group G, and we can construct a superposition of all states on single site. So this naturally symmetric states. Then we can have a Hamiltonian just project onto these symmetric states. And so this way, we obtain a ground state. So this Hamiltonian will have a ground state. And this ground state is just a product, direct product of these singlet states. So it's kind of a trivial states. Trivial means it's a direct product. Certainly it's a gapped, it's a symmetric. So this is a very simple situation. Here, I want to say that trivial actually really means non-topological. Non-trivial means something topological. Okay, and there is two definitions for the trivialness. There is a microscopic definition. That is, if a ground state is connected to a product state without experiencing phase transition, which close this energy gap. So this is this kind of lattice definition of a trivial state. Certainly, the state which cannot be connected to the product states will be called a topologically ordered states. So that's in some sense a definition of a topological order.
Sorry, when you say here connected, it means under local deformations?
Connected under the deformation for Hamiltonian.
But
the deformation which do not under local deformation of Hamiltonian. Hamiltonian always have a local interaction. Okay. This deformation do not close the gap, do not cause phase transition. If that ground state is connected to the product states, then we call that trivial. Otherwise, they are topological. So that's one definition for topological.
Okay, thank you.
And but however, in the traditional field theory, people usually do not want to talk about the lattice or UV completion. So whether we have a macroscopic definition, the macroscopic definition is a little bit tricky. And so one way to define this is the following: we can say that the ground states is a gapped and unique, but on any closed space manifold. Okay, so independent of a spatial topology of spatial manifold, the ground state is always a gap and unique. But that is not enough. Even if you only have give that, it's not guaranteed to be trivial. And we have to really say the following. And this non-degenerate ground state form a trivial line bundle on the coupling constant space. This coupling constant space means the deformation space of this local Hamiltonian, which preserve this energy gap. Or another way to say that, more using gravity language, like a moduli space of this closed space. The closed space may deform, and you have moduli space. And you deforming this moduli space of deforming coupling constant, if you get a trivial line bundle, then we say that is a trivial. However, it's not clear. We don't have a proof that these two definitions are equivalent. It's conjecture. We believe.
I'm sorry. MN, is it closed space in space as opposed to space time?
A space, just space. Space, only space. So this is a Hamiltonian.
Ordinary space.
Yeah, this is a Hamiltonian description.
And
yeah. This is space, not space time.
What is the modular space? The modular space is the space of coupling constants?
Yeah, space of coupling constant. If you think looking at Hamiltonian.
Okay, so not to be confused with MN.
No, yeah.
Okay.
However, you can think because of space, the metric on the space may be part of a coupling constant. So from that point of view, you can say it's a trivial line bundle on a moduli space, which parameterized by the metric of the space. So that's another way to say maybe the same thing, maybe not the same thing. So all this kind of conjecture. We try to see how to get a macroscopic definition. Yeah. So these are some ideas. Okay. Okay. So in this again, in this very simple symmetric example, what is a symmetry? Well, you say, oh, symmetry is just this. We have a symmetry transformation which commute with Hamiltonian. So that's the usual way to define symmetry. But however, there's another way to define symmetry by looking at the excitations. So what is the excitation? So here we try to say that excitation is a gapped ground state of the Hamiltonian with a trap. So that's with a symmetric trap. That's a keyword. We can add some kind of a trap, some symmetric perturbation, and this new Hamiltonian also have an energy gap. Then the ground state of this new Hamiltonian will be called excited state of original Hamiltonian. Okay, but here the new Hamiltonian may have a degeneracy ground state, and so more precisely, the excitation actually is a ground state subspace, if you want to be precise. Okay, but in this way, we parameterize all the excitation by this trapping Hamiltonian. And we have too many of them. So we can define types of excitation or equivalent class of excitations. And we say that two excitations are equivalent if their trap Hamiltonian can deform into each other without closing this energy gap. Okay, so that in this way we define so-called type of excitation. For our example, actually, it's pretty simple. The type of excitation actually is a representation of the group G. Okay, and so therefore, another way to describing this symmetry is to using the conservation law. But here, the conservation law of excitation actually is described by the fusion category. So some scary words. Okay, usually the fusion category have a, in our example, just described by the fusion of the representations. J1 representation, J2 representation may fuse into J3 representation, maybe with some direct sum. Okay. But to be more precise, actually, there's another data which is when you fusion 3 representation together, you fusion first two first, second two first. There's a basis change determined by F symbol. This F symbol is also a data for the fusion category. So actually, the symmetry the excitation or the conservation law more precisely not only described by the fusion rule, but also have this additional data of F symbol. These two data together is called the fusion category. So this is more precise. So using this conservation law, or more precisely, the fusion category, we can fully recover the symmetry group based on this so-called Tanaka duality theorem. That is this fusion category have one-to-one correspondence with this symmetry group. They can recover each other. Okay. So
Xiao-Gang, sorry, I have a question. So yes. Can you remind us the definition for symmetric fusion category? Does it mean that R1 times R2 is the same as R2 times R1?
Yes. Yeah, there's an additional thing that this fusion do not depend on which one is the first. RJ1, RJ2, RJ2, RJ1 is the same thing.
But then I'm
they
confused
behave like
by,
a boson.
But then the symmetric fusion category doesn't cover the non-abelian global symmetry of the system.
No, they do.
Oh, so why is that? Because I thought for a non-abelian global.
No, this is the fusion. This is the fusion rule of representation, not a transformation.
Okay, this is not for the group element.
Yeah, this is a fusion rule. The R is a representation. I'm sorry, R is a representation.
Okay,
R is representation. It's not group transformation. Okay.
And so I'm a little lost. So imagine I have just a free massive scalar field, right?
Yeah.
Let's say there are two of them. They transform. The group is O2.
Okay.
What are the symmetric traps that you're having in that case, and why do we get this degenerate?
So the trap means the trap itself cannot generate those particle conserved charge. So the trap can never be in the mixed state of charge 1 and charge 2. It's always eigenstate of a charge operator.
Juan, I think the purpose of the charge was to localize an excitation, because otherwise the excitation has a continuous spectrum.
Yeah, exactly. Yeah, the trap is really try to get this kind of gapped spectrum, and we can call the ground state.
I see. So you
excitation wave function.
So in that case, you would have a mass. You add a term phi squared where you locally decrease.
Yes.
And then,
for massless theory, this definition doesn't work. So that's it's tricky. Yeah, massless. This is only
for massive. Let's say it's massive.
Only for massive one. Yes.
Yeah. Okay. Okay.
It's only for massive one. So massless one will have a lot of problems using this way of thinking.
Let me understand. So you have this trap. So then in that particular case, you have two states, and you're talking about the.
So what is symmetry? Your symmetry is U1 symmetry. You think about
O2.
O2, yeah, that's the same as U1.
SO, yeah.
Oh, SU2, SO.
Well, okay, fine. Yeah, U1, let's say, yeah.
Yeah.
It's
so
because if the symmetry is G1.
So the trap may trap a particle with charge 1, or may trap a particle with charge 2, basically. So this 1 and 2, charge 1, charge 2 are those representations. For U1 case, they are one-dimensional representations.
Do you assume the delta H is also invariant under the same symmetry or not?
Yes. Yeah, it's very important. The delta H is a symmetric trap. It's a symmetric trap. So for the non-trivial example is that let's assume we have a SU2 symmetry. Let's consider we have a SU2 symmetry. So then the trap may trap a spin 1/2 particle. So that means the ground state of the trap must have a twofold degeneracy. There will be degeneracy. And so this twofold degeneracy really gave us a non-trivial representation of SU2. And this fusion of 2 spin 1/2 may give us spin 0 and spin 1 on this case. Yeah, so that is so this is a kind of more formal way, or maybe more rigorous way to define a symmetric excitation in gapped system with a symmetry. Okay. And
before you continue, is there any guarantee that such a delta H always exists?
Okay, yeah, this is a very important question. Is that yeah, I think for this simple example, they certainly always exist. But these definitions are really used to define so-called topological excitation. Sometimes delta H can trap an excitation, but the wave function cannot be created locally by local operators. It could be that we have a delta H trap something, and the wave function gets modified, but the modification is somehow global. There is no local operator in this neighborhood which can create such a wave function from ground states. So this is also very useful to define this so-called topological excitation. And for our case, what happens is the following: we may have a symmetric trap to trap a wave function, but however, this new wave function trapped by symmetric trap cannot be created by symmetric local operator. You have to use some kind of symmetry breaking operator to create those trapped wave function. So this, in some sense, a little bit of topological means even though everything is symmetric, but the trapped excitation cannot be created by symmetric local operator near the trap. So that's really gave rise to this non-trivial.
I'm confused about the logical order. Do you assume H and G and delta H, or do you assume only H and delta H and you find out that there is a G? Well, or do you start with G and find H, which is in
That's a very, very good question. So actually, using Tanaka duality, we can start with H and the symmetric delta H. So we know there are certain delta H are allowed. Then using this to define all the types. And then by putting two traps next to each other, we can really measure the fusion rule. And then we can using this way to recover the symmetry. So but basically,
that's why I'm confused, because
this is the way to recover symmetry without using transformation, without using any operator which breaks symmetry. Because
I think I understand that, but what's not clear to me is that if all you're given is H and you don't know about the symmetry group, how do you know which delta H to study?
Yeah, you have to know the delta H. Means that the H means you know the class of operator. I mean, you should know so-called allowed local perturbation. This local operator algebra. And H is just a wonderful operator, a sum of a symmetrical local operator. That's a give you H. But you do know so-called all the allowed local perturbation. This is the input. From this H and the allowed perturbation, you know everything.
Xiao-Gang, I'm confused. You start, when I asked you before whether delta H would be invariant, you pointed me to the phrase symmetric trap.
Yes.
But the way you present it now, there is no symmetry. There's an H, and you don't know anything about the symmetry group.
Yeah, but
the whole point of the second half of this slide is that you don't need to discuss the symmetry group. It will pop out automatically. But then yes, it's not clear what delta H is.
Yeah. Okay. In the usual language, if you don't have any symmetry, delta H will be any local operator in the lattice model. But here we imagine that we have some way to select so-called allowed delta H, which form a local operator algebra. And then we can discuss whether this local operator algebra have any symmetry or not. And certainly if you choose all possible operator act on this local Hilbert space, then have no symmetry. But if you select a subclass of operator, which is so-called allowed operator, allowed perturbation, then this subclass operator may have a symmetry. And so what I described here is a way to using fusion rule to determine the symmetry. So this is really the categorical point of view of symmetry without using transformation, but using this allowed operator, allowed perturbation, but not knowing what select those allowed perturbation. And so this is the way to find the selection rule, to find out this symmetry. So that is that's very good question. That's really indeed a different point of view to look at symmetry, and this point of view is called the categorical point of view, just using fusion rule. I don't know whether answer this question or not.
Xiao-Gang, may I have another quick question?
Yeah.
So let's take G to be SU2, for example. I think you also mentioned that example earlier.
Yeah.
Then is it true that rep G, the objects in rep G are labeled by the spin of the SU2?
Exactly, yes.
But then I'm confused by something. So then this category has infinitely many simple objects.
Yes.
So maybe it's not appropriate to call it a fusion category?
No, yeah. So this is again very good question. The symmetry G here in this talk are mostly finite symmetry. We have a continuous symmetry. There's an actual subtleties, and so many problems are open. Yeah.
Okay. All right.
Yeah.
Thank
so
you.
here we will do finite symmetry. Yeah. Thank you. This is a very important question also. Oh, why is that? Let me see. Why I have? Okay, yeah, it's very slowly updating. Okay, and so now let's consider another example. Actually, that's maybe echo Nati's question a little bit more. And so we consider a same model. We have a group element labeled states on each side, but we consider 1+1 dimensional model here. Okay, and but in this model, we have a different Hamiltonian. The Hamiltonian is given by this delta function. Basically, this Hamiltonian try to make all the ground state all labeled by same G. So like a ferromagnets. So it's a symmetry breaking states labeled by this group element G. Okay. So in this kind of symmetry breaking ground state, we know that we have a symmetry breaking domain walls. So we have on one half chain is G1, another half chain is G2, and then this domain wall are labeled by the group element, which is G1 times G2 inverse. They differ by the group multiplication. We call it G12. And this domain wall also have this fusion. G12, G23 became G12 times G23. So two domain wall can fuse. And so therefore, this domain wall also have a conservation law described by this kind of fusion. And this kind of fusion they call the fusion category, and have this denote so-called graded vector space, the G graded vector space. And so there's a mathematician have this studied this kind of fusion category pretty well. And so then we say, well, do we have whether this kind of a fusion correspond to a conservation law, or whether there is some kind of a symmetry correspond to this kind of fusion? Just a fusion of domain wall or conservation of domain wall in the symmetry breaking states. Or another way to say that we know that this rep G, this fusion category gave rise to this symmetry called the group G symmetry. And we ask whether this vec G, this fusion category gave rise to what kind of symmetry, and what is the symmetry transformation for this kind of fusion category. It turns out that we can describe this representation in the so-called dual model. In the original model, it's hard to describe this transformation, but in the dual model, we can do that. So this dual model is that instead of particle degree freedom on the side, we have a degree freedom on the link, the Gi plus 1. So we have degree freedom on each link. Okay. And the relation between the new degree freedom and original degree freedom is this Gi plus 1 inverse is a degree freedom on the link. So there's some kind of like there's some, well, I forgot, there's some duality transformation for the abelian case. This is kind of non-abelian generalization of that. Okay. And so under this, in the duality mapping, the dual Hamiltonian just given by this one. So therefore, the ground state is that in dual language, the ground state just the Gij just all equal to 1. Okay. And the excitation, the domain wall excitation just changing Gij equal to 1 to Gij equal to something not equal to 1. So that's the domain wall we just mentioned. Okay, in this dual Hamiltonian, we can see that this domain-wall fusion rule actually is can be enforced by this kind of symmetry transformation, which is basically Wilson line. If you think of Gij as like a gauge potential on the link, then this is basically Wilson operator. We pick a representation and make their product and take a trace, and we get a symmetry transformation. And the different representation gave us different symmetry transformations. Okay, but this kind of Wilson line transformation is do not form a group if G is not abelian. So they have this is non-trivial fusion. The product of two transformation is not give you third transformation, but there is a sum. Okay, but however, using this operator, you can still enforce this this transformation properties. Hamiltonian commute with Wj for all possible representation. So this symmetry requirement would enforcing the fusion rule. For example, this kind of changing Gij to Gij times H is not allowed. But however, if you do gauge transformation like we multiply H here, multiply H minus 1 here, this kind of transformation do not change this W, and this is allowed. So this is what enforces this fusion law. So therefore, this the fusion of a domain wall or the vector G, the vector G actually correspond to this kind of symmetry. Yeah. So we call this symmetry algebraic symmetry because of the symmetry transformation do not form a group. Okay. And I think in conformal field theory, people using defect line to discuss symmetries, to represent symmetry. And there's a discussion of a non-invertible defect line. So this is algebraic symmetry is exactly correspond to this non-invertible defect line symmetry. Okay.
Xiao-Gang, let me can I make sure I understand the notation? So W's are objects in rep G.
It's a Wilson line. It's given by the rep G. Oh, okay. Representation. It's given by the representation. You choose representation, you can construct this Wilson line operator. And I don't want to say whether it's in a rep G or not. They are not object rep G. It's labeled by object in rep G, certainly. But here it's just operator acting on the whole system.
But the fusion product is satisfied.
Yeah, this fusion is
product
as a representation. Yeah, the fusion is the same as a representation.
Is this related to the non-symmetry lines that Xiao-Gang
non-invertible symmetry line. Yeah, non-invertible.
Xiao-Gang collaborators study.
Yeah. It's a non-invertible defect line.
Yeah.
So it's exactly the same as what they said.
Here, you pattern in 1 + 1 dimension is the exact same thing. But certainly this one, this kind of thing also happen in any dimension. Yeah. So here, my point is that if you want to say vector G is a fusion category describing conservation law, and their corresponding symmetry will be this kind of algebraic symmetry, or this non-invertible defect line, or defect membrane, or something in higher dimension. And here, vector G is a little bit scary, so sometimes I'm using the G tilt to describe this dual symmetry. Yeah. So therefore, we see that for the one-dimensional system with the symmetry G, their symmetry breaking state have a domain wall, and the domain wall would have a conservation law which describe this dual symmetry, or this algebraic symmetry. So those are examples of a symmetry and algebraic symmetry. And also we have this symmetry and the dual symmetry. This G is a symmetry and the G tilt is a dual symmetry. Or maybe you can say the rep G is a symmetry, a vector G is a dual symmetry. Okay. So we can put these two things together. Say we have a symmetric Hamiltonian, just this one projecting to trivial product states, or we can have another term which give us a symmetry breaking state. Putting these two together give us some kind of a phase transition. So if B is large, we have a symmetric ground state. If J is large, we have a symmetry breaking ground state. Basically, it's this picture. So we have a symmetric ground state or symmetry breaking ground state. But that's for the symmetry G. Okay. But however, for the dual symmetry, so this is for symmetry G. But for the dual symmetry, we have some kind of complementary picture. That is in a symmetric states, it's a symmetry breaking state for the dual symmetry. And the symmetry breaking state for G is a symmetric state of a dual symmetry. Okay. So so we have this this kind of duality picture. Okay. And so here I want to define what is a spontaneous symmetry breaking a little bit more carefully, because usually for the symmetry we know how to define that, but for the algebraic symmetry or for higher symmetry it's a little bit trickier. Okay, so one way to define that microscopically is that we have a degenerate ground state for some topology of a closed space, only space. Okay, for some space have a degenerate ground state, which the space have no boundary. And also on these degenerate ground states, some symmetry transformation do not act like identity. It's not proportional to identity. And so these two features define so-called spontaneous symmetry breaking. Okay, and so the Hamiltonian okay, so the picture for this symmetry and the dual symmetry is the following: that the Hamiltonian actually have both symmetry. Hamiltonian as an operator have both symmetry, but just one of them are spontaneously broken. So the ground state don't have symmetry. Okay, and these two symmetry actually is kind of strange. There's some kind of exclusive. That is if you consider gapped states. If you consider gapped states, then one of the symmetry must be spontaneously broken. Okay, and but however, at the critical point, you can see that this critical point is touching the symmetric states for G and touching the symmetric state of a G tilt. So they touch both. So we say this critical point have both symmetry, have both G and G tilt. So this is another very interesting. That the ground state which have both symmetry, if both symmetry are not broken, this ground state must be gapless. Okay, and Michael Levin studied this kind of exclusive symmetry very carefully for some abelian group. Okay, and so therefore we can say that this critical point have both symmetry, have both G and G tilt are unbroken. But however, so we want to put these two symmetry together, and we call them categorical symmetry. So that's one definition, very naive definition of categorical symmetry. We try to put all the symmetry together. So this symmetry and the dual symmetry together. But this putting them together is not just a direct product. This G and G tilt are not independent. In some sense, they have a mixed anomaly. So you can view V as a mixed anomaly. So they have a mixed anomaly. So this mixed anomaly means that in order for state to have both symmetry, they have to be gapless in one dimension. So they have mixed anomaly. And, yes.
Sorry, is it a good point to ask a question?
Yeah, sure.
So let me take the example where G is Z2. And let's say we are looking at the Ising transition
exactly.
in 1D. So G delta can be viewed as the Pontryagin dual of Z2.
Exactly.
In this case, that's isomorphic to another copy of Z2.
Exactly.
The isomorphism is not canonical.
Yeah.
Now, in this particular case, Vec G is just a Z2 fusion category.
Exactly.
And Wrapped G is also a Z2 category.
Exactly.
However, at the gapless point, namely your black dot, that's the Ising CFT. Ising CFT in 1+1D is known to have the Ising category.
Yes.
So so I'm trying to understand the category at the lower left of your slide. This Wrap G upper wedge with Vec G. So
okay, yeah.
Are you saying that in the special case when G is Z2, Wrap Z2 upper wedge Vec Z2 is the same as the Ising fusion category?
No. So you really had.
Oh, okay.
Ahead of my talk. Actually,
yeah, I'm still trying to understand this wedge.
Yeah, it turns out that this critical point have several description. One description will describe this critical point as a boundary of a Z2 gate theory. So it's really the boundary of Z2 gate theory. But however, this critical point also can be viewed as the boundary of a double Ising model.
Yes.
And you're describing this double Ising model.
But so is the
since you asked this, let me answer your question. Since you already asked. So here we only consider this is a very, very good question. We only consider Z2 tilt. But actually, at the critical point, we have another symmetry. We call this Z2EM.
But that's not the Z2 symmetry. It's a Z2 symmetry of the 2 plus 1D topological order, not the Z2 symmetry of the 1 plus 1D
Z2EM. But at this critical point, this may be emergent. You know, these are the 1 year, weekend 1 year duality. Yeah, we view this weekend 1 year duality as a symmetry.
I understand. Yes, I understand.
But in other place, we don't have this symmetry. This is not.
I understand.
But at this point, you either include this Z2EM or not include it. If you include that, you get the Ising critical point. If this picture, I do not include this. I only consider these two. Then I get this boundary of a Z2 gate theory.
But maybe let me ask a more concrete question. So on the lower left of your slide, you have this rep G, wedge, vec G.
Yes.
Is that the fusion category or is that the modular tensor category?
That's again, I will explain that later. This actually this is supposed to be a modular tensor category in one higher dimension.
Okay.
And this particular one is this Z2 gate theory modular tensor category.
I see. So
not
the
double
lower
Ising. But however, if you include all these symmetry, including Z2EM, and there's a even bigger category of symmetry, and that is double Ising.
I see. So let me not include the E and M. So am I correct that in the more general case, rep G, wedge, vec G is the Drinfeld center of either one of them?
Yes, exactly.
Okay, thank you. Okay, that's what I wanted to know.
Yeah, that's a picture.
Can you give a more lowbrow version of it? I thought that Ising model has one Z2 symmetry, not two. And if I try to translate it to language I understand, then the Z2 I know is getting order, and the other one is the disorder one.
Exactly. Yeah.
There's no such symmetry. The Hilbert space does not have any other Z2 active.
You're totally correct. So this is kind of you're totally right. There's some tension. On one hand, it looks like we have a Z2 symmetry and this disordered Z2 symmetry. We naively want to put them together. On the other hand, you are totally right. As a symmetry requirement, one Z2 is enough. This G is enough. We don't need another G tilt because this G is already specified Hamilton symmetry class of Hamiltonian. But on the other hand, I feel that it's still useful to include all the possible symmetry. It's kind of just maybe at this time, just for mathematical point of view. You know, this point, we can either say it have this G symmetry, or we can say the G tilt symmetry. Which one to choose? Don't know. So let me include them both. You can just say just for that purpose. But I do feel that this way of looking at the symmetry have some advantage, and so maybe later we hopefully you can get there. Yeah. And
can I have a quick comment in response to Nati's question? So let me just give a slightly different perspective on what you are saying here. So I think from a purely 1 plus 1D point of view, the Ising CFT has a unique Z2 symmetry. But in addition to that, there's a non-invertible topological defect line, and that's related to the Kramers-Wenier. But from this perspective, I wouldn't call the non-invertible Kramers-Wenier duality line a Z2 line because it obeys the non-group-like fusion rule. And I think what you are advocating here is to couple this 1+1D system to a 2+1D topological quantum field theory in the bulk. In the particular case of Ising CFT, the bulk is a 2+1D Z2 topological order. And once you couple it to the bulk, then the Kramers-Wenier duality line can be thought of as a Z2 zero-form symmetry of the 2+1D topological order.
Yeah, there's a, you can also view that way. Yeah, actually that's a point.
Thank you for answering my question.
Yeah.
I think maybe we should let Xiao-Gang proceed with his talk though, because
I
think we're asking questions, some of which might be answered on later slides.
Sure. Okay. And so for the next question, actually this is symmetry G and G tilde are really not independent. So they are so-called dual equivalent. And so here we say that suppose we have a symmetry generated by this W. And we can define this algebra of symmetric local operator. Means the local operator which commute with this symmetry transformation. And then we say that and then we have this two symmetry, this G given by ordinary global symmetry, or this G tilde, this algebraic symmetry given by this Wilson-line operator. And we try to claim that these two symmetries are equivalent in the sense that their operator algebra have a one-to-one correspondence. They are isomorphic algebraic operator algebra. So in this sense, this G symmetry and G tilde symmetry are kind of equivalent, or the dual equivalent. So this really the comment on this lattice question, that is one of them is enough, or they specify operator algebra. We don't need another. So these two symmetries are not independent. In this case, they are even equivalent to each other in some sense. Okay, but still, somehow the critical point contain both of them. I mean, in a sense that as a ground state, these two symmetry G and G tilde are both unbroken, and this is a very important feature for the gapless point. Actually, the reason we emphasize this is really because we feel that maybe this is a very important property for critical point for gapless states. Basically, if you include all the symmetry and the dual symmetry all together, maybe you get a pretty good description or characterization of gapless states. And so this is wishful thinking at the moment. Certainly, we are hoping maybe after years we may have some theory like that. Okay. So so far what we did is just a 1+1D version, and certainly all we talk about can be generalized to higher dimension quite straightforwardly. Like this algebraic symmetry can be generalized to the algebraic higher symmetry, and this fusion category to describe a symmetry or to encode symmetry can be generalized to this so-called fusion higher category to encode symmetry. So here I just want to say that like in 2+1 dimension, okay, the excitation can be string-like excitation or point-like excitation, okay. And then the deformation of a point-like excitation is a local operator or symmetric local operator. So these three layers of things form a so-called two category. This string-like excitation corresponds to object in the category, and the point-like excitation or this domain wall on the string is so-called one morphism connecting two objects. And this local operator connecting this a particle borderline in space-time is a two morphism. Okay, like a domain wall on the borderline is a local operator. There are two morphisms. So this in 2+1 dimension, we only have these three layers. Putting these three layers together, we got a so-called a fusion two category. Yeah, this fusion two category naturally describe excitation in 2+1 dimension. So similarly, so we can say that for the Z2 symmetry, let's say for Z2 symmetry in 2+1 dimension, we want to use a fusion category or fusion two category to describe it. And so what is a fusion two category? It turns out that the fusion two category is this so-called two rep Z2. This is something we are quite familiar with, actually. But here I'm describing that in a more formal mathematical way, make it less familiar. So certainly in this fusion 2 category, we have a 2 morphism, just a local operator. In this case, just a Z2 symmetric local operator. And we have a 1 morphism. And the 1 morphism just a Z2 charge. This E is a Z2 charge. Something carry Z2 representation. And we also have a 1 is a neutral Z2 charge. So that's a trivial excitation. But however, this Z2 charge and the trivial excitation can be viewed as domain word on the trivial string. Okay. And certainly we have a string like excitation. We have trivial string is nothing. But actually, we can have a string formed by this gas of a Z2 charge. Actually, the Z2 charge may form a 1-dimensional gas. And this 1-dimensional gas is a quantum liquid. Actually, they form a spontaneous symmetry breaking state of this Z2 symmetry because this E have this mode 2 fusion rule. So this Z2 charge have a mode 2 fusion rule, have a mode 2 conservation. So their liquid may break this mode 2 conservation, that's a symmetry breaking. So therefore, we have 2 types of a string-like excitation, the trivial one and this Z2 symmetry breaking states. And so mathematically, this kind of a thing form a so-called fusion 2 category. That's we call the 2-rep Z2. And similarly, we have a 2-rep G. The Z2 can be any symmetric group. So the claim is that in 2 dimension, in 2 + 1 dimension, the Z2 symmetry is encoded by this 2-rep Z2. Okay, and so sometimes we also call 2-rep Z2 just Z2 symmetry at the symmetry wise. So those are basically higher dimensional generalization of what we discussed. It's just the idea is the same. We just generalize to higher category. But the description of higher category is very tricky. So involving this kind of descendant excitation. So this is just example. This is one of the simplest higher category. Okay, and so certainly this in the same token, we can have in 2 + 1 dimension, we can have a G spontaneous symmetry breaking states. Okay, in this spontaneous symmetry breaking state, we have a string-like excitation, which is just the domain wall between different degenerate ground states. Okay, and this string-like excitation may have this their fusion rule, like a charge object and fusion. So this gives rise to this so-called algebraic 1 symmetry, because this is really like one form symmetry, because the charge is a string-like, so that's a 1 symmetry. Okay, it's algebraic because their fusion is not abelian. Have a direct sum. Their fusion is not so-called pointed, have a direct sum. And similarly, the symmetry transformation is generated by this Wilson line operator, which act on a loop in a 2-dimensional space. Okay, and so this is analog of this, and so we have this a 2-rep G describing the algebraic 1 symmetry, and this algebraic 1 symmetry actually is this 1 form symmetry if G is abelian, which is really discussed in this paper, and that's really lay out all this higher symmetry and the analog with a global symmetry and all this physics. And so this is a generalization of this higher form symmetry. For the non-abelian group, we may hire so-called algebraic higher symmetry. So this is some generalization for that. And the generalization really because that the higher symmetry are described by higher group. But this algebraic higher symmetry is a little bit beyond the higher group. It's something slightly more general than the higher group. Okay, so those are basically the example. And so we have this all this example of new symmetry.
Sorry, I missed something. Is G abelian? Oh, G is abelian. Okay.
If G abelian is a higher form symmetry. If G is non-abelian, you get something a little bit extra. Okay. So those are examples. Okay. And so next question is that what is the general theory? What is the mathematical theory for this kind of algebraic higher symmetry. It's not a group, it's not a higher group. Then what? What is beyond the higher group describing this kind of algebraic higher symmetry in a systematic way? And here the idea is that we want to use a fusion category to describe a symmetry, just like this. We have this two vector G describe this algebraic one symmetry. Okay, and but however, using fusion higher category, we have a problem. Sometimes a fusion higher category describe a topological order without any symmetry. For example, let's consider in 3+1 dimension G gauge theory. And we have this point like a gauge charge. That's a point like excitation. We have a string like a gauge flux. Assuming G is finite. Okay, here GO is finite. And therefore, this point excitation and the string excitation also form a higher fusion category. And we denote this higher fusion category in this formal notation, just a G gauge theory. Okay. But this higher category have no symmetry. This have nothing to do with the symmetry. It's just a topological order. So therefore, only certain kind of fusion higher category theory describe symmetry. But other fusion higher category don't describe symmetry. So we have to say which one describes symmetry, which one do not describe symmetry.
Xiao-Gang, can I ask for this bullet point you are just mentioning? So in 1+1D, for symmetry in 1+1D, is the mathematical statement of this bullet point just that not every modular tensor category is the Drinfeld center of some other fusion category?
No, in 1+1D, let me see.
Xiao-Gang, is that actually true?
Not every modular tensor category is a Drinfeld center of a fusion category. That's a true statement.
That's true statement. There are certainly modular tensor category who don't have a gapped boundary.
That's right.
Yeah.
So is that the answer to your first bullet point in 1+1D?
Actually, 1+1D. There's no topological in 1+1D. So I think.
Oh, sorry, I meant 2+. So symmetry in 1+1D, but category in 2+1D.
I think every fusion category probably describes symmetry. Some kind of algebraic symmetry, yeah. Because in 1+1D, there's no topological order.
Okay.
And
right.
so every fusion category can be viewed as a symmetry.
Okay, I see what you mean. Okay.
But I'm not sure, but I'm thinking that in that direction. But
I see. I see.
Okay, that's my guess. Let me put it this way. But in higher dimension, we could have a topological order.
Right.
Like a modular tensor category in 2+1 dimension cannot be viewed as symmetry, describing 2+1 dimensional symmetry.
Oh, I see what you mean. Okay, I see what you mean.
That's what I mean. Okay.
And can I have a question on the previous slide? So in 1+1D, you discussed the Tanaka duality that relates rep G, vec G. Can I think about it as the statement that the two fusion categories have the same Drinfeld center?
Yes.
Then is there an analog in 2+1D for 2 rep G and 2 vec G?
Yes, that is the picture. Actually, I don't know where I can get there or not. Yeah.
Oh, okay.
That's a holographic. So far, we are doing categorical point of view.
Yeah.
Okay.
There's also a holographic point of view for all this story.
Let me suggest that some of these questions we'll have more time for at the virtual tea time at 4.
Yeah.
Oh, okay. Sorry.
Okay. And so therefore, the question is which fusion higher category can be viewed as symmetry, which one cannot? Okay, that is the question. And here we say that in order for the fusion category to be viewed as a symmetry, describing a symmetry, the symmetry can be broken. We can break the symmetry to nothing. Okay. And so therefore, if you don't have any symmetry, if you don't have a topological order, then the excitation are described by this n-vec. This n-vec describing excitation in the product states with no topological order and no symmetry. That's n-vec. However, if you can reduce the fusion category into n-vec, then we say, well, this symmetry can be broken. Then we say those fusion category is correspond to symmetry, or this algebraic symmetry. So this introduces a notion in mathematics called the local fusion N category. So basically, that this is very formal, which actually I also myself don't understand very well. Those are my mathematician collaborator tell me this. And so basically, there's some kind of functor. This functor is top faithful functor, which I don't really know what it means. And so they can map this fusion category, fusion hierarchy category into N vector. Physically, which I know that this top faithful really means that you know that at top level, the morphism at top level is actually the local operator. So this functor basically map the top morphism like an embedding of a top morphism, like this injective mapping, map the local symmetric operator to local operator. You know, it's kind of embedded into this local operator. So at the top level, we have this mapping. At the other level, we have a similar mapping, which must be consistent with this top level mapping. And whether there's some additional condition, I don't know. Yeah, but at the moment, we are thinking there's some notion like so-called local fusion category, which admit this kind of a functor, and this kind of local fusion category can describe this generic algebraic higher symmetry. So maybe this is a very general way to look at the symmetry. So basically, local fusion category just play a role of group. So we are hoping this kind of notion fully describe all the fusion N category. All the algebraic higher symmetry. Okay, and so maybe let me just probably I can using 10 minutes try to summarize the second point of view. That's okay.
Yes.
Yeah, and so actually, what I described so far is a categorical way to describe algebraic higher symmetry using this so-called local fusion higher category. Actually, there's a holographic way to describe this algebraic higher symmetry, or the more general higher symmetry. And so to describe this, so let's ask another question. We say, which fusion higher category describe a topological order without any symmetry? You can see what we discussed before is another extreme. We say, which fusion higher category describe symmetry but no topological order? Here we say which fusion category describe topological order and no symmetry. Okay, so this is related to so-called anomaly, means that a fusion category describe a topological order without symmetry if this describe excitation in the bosonic lattice model in the same dimension, and but without any symmetry. That's almost the definition. I'm repeating myself. So we have, if a bosonic model with no symmetry, but have a non-trivial excitation, and those kind of excitation form a so-called fusion higher category, and those are for the topological order. But however, there's another way to say that, you know, when we have a lattice model realization in the same dimension, it can be viewed as a boundary of a trivial product states, because when you have a model which is well defined by themselves, it can always be viewed as a boundary of a trivial product states in one higher dimension. Okay, so we're using this condition that this fusion category can be realized as a boundary of a trivial product states in one higher dimension. Okay, so this is related to this holographic principle for topological order. So that is for any fusion category, as long as it's properly defined, some fusion category, they can always be realized as a boundary of something in one higher dimension, but some topological order in one higher dimension. Okay, and there's another conjecture is that, and this correspondence is many to one. So that's this boundary fusion category uniquely determine the bulk topological order. But we could have several boundary fusion category give rise to same bulk topological order. If a boundary is 1 + 1 dimension, bulk is 2 + dimension, this relation is a Drinfield center, which Shu Heng already mentioned. And we believe there's a higher dimensional version of that. And so therefore, this dream field center or this higher dimensional generalization of dream field center is denoted as this. We have a boundary fusion category determine the bulk topological order. And these bulk are properly topological order. So the dream field center, double dream field center, if you do that twice, if you do center of center, it's trivial. Okay. And so therefore, so now, and let's assume this dream field center can be properly defined mathematically. If you give me a fusion category, we can always define the dream field center. Okay, can't compute the dream field center. This is again the mathematical problem which people are working on. And then if you do know this answer, then we can say that the condition for the fusion category to describe a topology without symmetry is that their dream field center or some generalization of dream field center is trivial. Okay. And so this is kind of answer the question, what is a topology order without symmetry? And so without symmetry means that the dream field center is trivial. Okay. Now from here, you can see that what is symmetry? From this point of view, is very interesting. We have another point of view of symmetry. That is, if you have something like fusion category whose dream field center is not trivial, then this non-trivialness means symmetry. Basically, if M is trivial, that means C have no symmetry. If M is non-trivial, then we say C have a symmetry. So basically, rep G, vec G, their dream field center is non-trivial, and that is a symmetry. Okay. If we have some kind of fusion category whose dream field center is trivial, then we say it have no symmetry. And this dream field center basically like computing anomalies. So from this point of view, we almost like to say that if a fusion category have a dream field center non-trivial, have anomalies, then it have a symmetry. If no anomaly, no symmetry. So this also related anomaly to symmetry. So the bottom line is that we relate symmetry. We relate symmetry to topological order in one higher dimension. And a topological order in one higher dimension is also referred as an anomaly. So all these concepts somehow get related. So here I just want to say this: there's a relation, but exactly how they're related. So let me just using this example, because this relation is very abstract. So let's using this one example to really describing this relation. Why the symmetry and the topological order in one higher dimension and the dream field center are related, how they are related. For example, let's consider in 2+1 dimension, we have a Z2 symmetry. And we know that it's related to this fusion 2 category, this 2 rep Z2, okay. And in the holographic point of view, this symmetry should be related to the 3+1 topological order, which is the dream field center or generalization of dream field center of this 2 rep Z2. Okay, and it turns out that this dream field center is really computing the bulk. We say which bulk topological order have a boundary describing by this 2 rep Z2. The answer is very simple. It's a 3+1 dimensional Z2 gauge theory with both Z2 flux and Z2 charge. Okay, so this is the picture. And we have Z2 charge, which is called E, that's a Z2 gauge charge. And the Z2 flux we call S. Okay. And one of the boundaries that this Z2 flux condense, that's give rise to a boundary. And this boundary we only have a Z2 charge. And this Z2 charge can move around on the boundary, they can fuse and they can braid, etc. Actually, this Z2 charge on the boundary is precisely this 2 rep Z2. Okay. So from here we can see that this 2 rep Z2, this symmetry associated with a topological order in one higher dimension, which is just a Z2 gauge theory in one higher dimension. Okay, and also this conservation law of Z2 charge is kind of coming from the conservation law of Z2 charge in one higher dimension. This Z2 gauge charge, their conservation law produce the conservation law on the boundary, which is Z2 symmetry charge. Okay. And we don't see, and this conservation law of this Z2 string in the bulk is a Z2 1 symmetry. and which is not shown in the boundary because the Z2 string condense. So this symmetry is this Z2-1 symmetry is spontaneously broken. So we don't see that. So we only see one of them. Okay. So this is how symmetry and the topological order in one higher dimension are related. And we can also see clearly that we may have another boundary that where Z2 charge condense, but the Z2 string don't condense. And in this case, the boundary would have a Z2-1 symmetry. And this is precisely the dual symmetry described as 2-vec Z2. This Z2-1 symmetry is a 2-vec Z2. Yeah. And so that's a dual symmetry. So therefore, that's really the echo the picture we described before, that somehow this Z2 symmetric system have both Z2 symmetry and Z2-1 symmetry. Okay, they have both, but just one of them are spontaneously broken. However, this Z2 symmetry and Z2-1 symmetry are not independent because in a bulk, this Z2 charge and Z2 flux have non-trivial mutual statistics between them. This AB phase between them. And so this non-trivialness is this V, this anomaly. So they are not independent. They somehow coupled in a certain way. And because this non-trivial coupling or this mixed anomaly, we cannot have a symmetric states where both symmetry are symmetric. We cannot have symmetric gap states for both symmetry. Now, for gap state, one of the symmetry must be broken. But however, we can have a gapless states. You know, this Z2 gauge theory have a gapless boundary where nothing condense. If nothing condense, this boundary must be gapless, and this gapless boundary is this have a full categorical symmetry. So from here we can see that the so-called categorical symmetry, putting these two symmetries together, actually more precisely should be viewed as a bulk topological order. Categorical symmetry is a bulk topological order. So this fusion rule and the braiding in the bulk topological order fully encode the so-called categorical symmetry. That's how we put these two symmetries together. And then the boundary of a bulk topological order, if nothing condense, they are gapless. Usually the gap boundary is coming from condensation. If nothing condense, we may have a gapless boundary, and this gapless boundary have a full categorical symmetry. So this is kind of holographic way to view symmetry and the categorical symmetry. Okay, so maybe we can skip that, and we can skip this. So this holographic way is actually it's very useful. For example, we want to suppose we have a algebraic higher symmetry describing by this higher fusion category R. Okay, and there's the issue of how to gauge them. Okay, so I want to using this holographic picture try to understand how to gauge this algebraic higher symmetry. Okay, and one way to gauge them is usually, if you know symmetry transformation, we gauge them. But here in the categorical point of view, we do not know symmetry transformation, so it's not easy to gauge them. But however, as I mentioned, that this algebraic higher symmetry have the bulk. Their dream field center actually give you a bulk topological order, which correspond to their categorical symmetry, or this bulk topological order. And then we can consider a slab of this bulk topological order. And one boundary is R, the lower boundary also R, but with a reverse orientation. Okay, and so putting these two together, actually we form a system, and this system actually corresponds to gauge the R symmetry. Suppose we have a symmetry. If you have a system with R symmetry, if we gauge them, we no longer have symmetry, but we have a topological order. Okay, we have some kind of category theory describing topological order. So I want to say that the topological order obtained by gauging the R symmetry is given by this construction. And there's the R symmetry have a bulk topology order, have another this fusion category boundary, another fusion category boundary, the plus bulk topology order, the stacking them together. This give you a topology order correspond to R gauge theory. So this is one way to look at gauging symmetry. And the dual symmetry, using the gauging symmetry, we can see we have a symmetry, we have a dual symmetry. Using the same construction, we can define what is dual. Dual is that if I have a R, we have this bulk. We have R tilde have the same bulk. But R tilde together give us the trivial states. If they're stacking, give us trivial states. Then we say R and R tilde is a dual symmetry. And so actually, this rep G and vec G have this property. So they are dual to each other in this sense. Okay. And maybe the last example, let me just say that you can see that these dual symmetry are equivalent. Also say that the symmetry and the dual symmetry are in some sense equivalent because they have same bulk. And this is a more general statement. Suppose we have a symmetry described by R, another symmetry described by R prime. Okay, they're both a local fusion higher category. If they have same bulk, we say they are dual equivalent. Okay, so we can just compute their dream field center and to see whether the bulk is the same. Then we can use this to define the equivalent symmetry. The example will be this rep G, vec G will be this equivalent symmetry. Yeah. So actually one can also have this equivalence of low energy effective field theory. I won't discuss this. So I think I should stop here. Basically, if there's a symmetry, have this categorical point of view, but I think this holographic point of view is more appealing. It seems to capture the better essence of the symmetry. Thank you very much.
Thank you, Xiao-Gang.
Yeah.
Well, we certainly have time for some more questions, which you can ask now, and then those who want to really ask a lot of questions will reconvene at 4 for virtual tea.
So in the end of the day, these symmetries, is the Hilbert space in representations of it? Are there constraints on correlation functions because of it?
Yeah, I'd rather using the second picture, some constraint, you know. In some sense, I try to say that the symmetry, using this categorical point of view or in some more general point of view, the symmetry is a way to select a subset of a local operator. Using the commutator or commutant is one way to select a local operator. That's a usual way, using transformation to select local operator. And maybe there's other way to select local operator. So actually, this holographic way is also can be viewed as a way to select local operator because of the boundary operator, the local operator on the boundary for topology order, somehow they already satisfy certain selection. Their operator algebra have influence from bulk topology order. So therefore, this boundary operator is a class of a local operator, and then there's you can use symmetry to select another class of local operator, and these two classes may be isomorphic and as an operator algebra. So this is maybe the way to understand why the bulk topology order have play similar rule as the symmetry. The symmetry transformation and as a boundary operator both can select a subset of a local operator and have a different local operator algebra. I think this point of view maybe is better, but we don't have any theory along this direction. You're using the local operator algebra language to really view this. Yeah, I feel that may be a better language to see this.
Another question is about the use of the phrase duality at the bottom of this slide.
Yeah.
Can I just think of it as adding scalar fields in the adjoint and Hicksing SUN to ZN? Or is there more to it?
This probably is well known. Unfortunately, I'm not very familiar with those. I didn't really follow all these papers. So many papers in this. So basically, the one application of this dual isolohoric defective theory is that this SU1 gauge theory without gauge charge is equivalent to this center symmetry. This Z2 gauge theory without gauge charge. But basically, without gauge charge really means that you do allow the gauge charge in the joint representation. That's a field strength is always there. So basically, the SU1 gauge theory with a gauge charge in the joint representation are also equivalent to this ZN gauge theory without gauge charge.
Well, it's not equivalent. There is a phase of the system where you
exactly. They're not equivalent. So basically so here when I say equivalent really means that there is a phase. I really mean the same anomaly, basically. They two have same anomaly.
Well, so, but then it's the same statement that you can Higgs one theory to the other.
Yeah, exactly. Yeah, you can have phase transition from one theory to another. So basically, you're adding perturbation to one theory, adding perturbation to another theory. These two deformed theory can have one-to-one correspondence. Yeah. But however, certainly it is also well known that if SU1 gauge theory with a fundamental gauge charge, they are equivalent to local bosonic model, like a scalar field theory with no symmetry.
Yeah, you just add you add a scalar in the fundamental and you Higgs the SUN.
You Higgs everything, then nothing survives. So yeah, so this is this is a way to say that there, because these two theories, one have a trivial bulk, another have a non-trivial bulk. So it's just a simple example for this picture.
Well, I have a question that'll show that I didn't understand the story very well. But is there a systematic procedure given a boundary theory to determine what the bulk theory is supposed to be? So to be specific, suppose we took SU2K, but it's not very nice, it has a framing anomaly.
Yeah.
So it has n copies of SU2K to cancel the framing anomaly. So is there in principle some procedure that will tell us what's a four-dimensional theory that has n copies of SU2K on the boundary?
I don't know. Yeah, maybe. Actually, I'm hoping to develop this kind of thing via examples. But I want to say that for general mathematical theory, if you know the fusion higher category, to compute this center is very difficult. But the mathematicians now realizing this is an important question, so they are doing that. For the fusion one category, that's a fusion category, to compute the center, that is a more well developed many years ago. That's called the Dreamfield center. But for the fusion two category, to compute it's a center like some three category, and people started writing paper in this, and those are really a very abstract mathematical category theory. But on the other hand, in physics, I'm hoping that we can work on some examples, like what Edward mentioned, that there are some well-known examples. Then we can using those examples to directly construct the path integral or Hamiltonian in one higher dimension. And in this degree, the answer is yes. There is some kind of fusion category which are described by this some data. Okay. And then one can write down some tensor network path integral using the data of a fusion category on the boundary. You can write down the one higher dimensional tensor network path integral, which really realize the bulk topology order. Okay. This is done in 1+1 dimension to 2+1 dimension. I think a similar thing can be easily generalized to higher dimension because the procedure is pretty straightforward.
That assumes that you do have a local path integral for the theory you want to start with.
Exactly. So the difficulty is that what is the data to describe a fusion higher category? This part is very complicated. But if you consider some subclass of a fusion higher category, maybe we know there's some data describing them, and using this data, you can using this data to directly construct this tensor network path integral. Actually, this kind of thing is like this, Dagwar-Witten model is kind of belong to that. It's you have a path integral, you have some group element and link some kind of phase factor, and etc. And those are really coming from the data in the fusion category data on the 1+1 dimensional boundary. And so this kind of construction can be really generalized. And the main I feel the construction is easy. The difficulty is that we don't have a most general description of a fusion higher category. And whatever we have is some concrete description in some subclass of fusion higher category, and their bulk can be computed. So this part probably can be done. Yeah.
Thank you. More questions?
I have a quick question, Xiao-Gang. Maybe you said this and I missed it, but what is known just mathematically about the classification of these things? I mean, is there a question, the sort of analog of fine structure constants FABC that satisfy the Jacobi identity? So there's some sort of a problem of that character. Is there some known classification, even putting some constraints? What's known mathematically about what the set of these things actually is?
Yeah, there are many classifications. So let me just say one thing. That's what is a higher category? Yeah, so basically, how to classify all different algebraic higher symmetry? Then I just mentioned that maybe this local fusion N category is a way to classify all possible algebraic higher symmetry. But there's other classifications. And for example, you say how to classify a gapped phase matter with this algebraic higher symmetry? How to classify topological order with this algebraic higher symmetry? Actually, we have some kind of a proposal for that. And so I don't have time to talk about that. And there also, for algebraic higher symmetry, there's also symmetry protect symmetric states, these SPT states, and how to classify them. And there's another proposal to describing that. And things like that. And so certainly the most interesting thing would be that whether this kind of thing can be used to understand a CFT, this gapless CFT. And so maybe I just want to say that we know that in the ADF CFT correspondence, we have a saying that if a bulk have a G symmetry, then the boundary have a G symmetry. Boundary CFT have G symmetry. But here we say something a little bit more precise. That is, if a bulk is a pure gauge theory and nothing else, then the boundary happen to be this symmetry breaking critical point. This particular critical point. Okay. So this correspondence. So therefore this bulk really representing the categorical symmetry, the bulk topological order, and we are really hoping that this knowing this bulk topological order, we somehow more or less determine the boundary CFT. So in terms of constraint and usefulness, I'm really hoping this line of thinking may be useful. That knowing the symmetry, knowing all the symmetry, categorical symmetry, I mean knowing bulk topological order, we can somehow more or less determine the boundary CFT. And this may be one way to understand the CFT in a systematic way.
I have a question. On the previous slide that you showed, you said that higher order symmetries are classified by higher groups. How do you construct those higher groups?
Okay, yeah, and so let me see. Okay, I have one example. So let me just give you one example for this. Okay, yeah. So here we have a so-called one-form symmetry. We have a one-form symmetry, but with a Z2, this one-form symmetry have a string. This string have a Z2 fusion rule. The two strings can annihilate. but the single string cannot disappear by themselves. So it is mode-2 fusion, mode-2 conservation of this string. So string have Z2 fusion. So this kind of one-form symmetry, Z2 one-form symmetry, are described by these two groups. These two groups have a classifying space where the pi2 is a Z2. The pi2 is Z2, but the pi1 and the pi3, pi4 all trivial. So this is one particular way to say one-form symmetry under this classifying space of the higher group are really related to the symmetry. So this is an example to see how they related. I feel this may be the simplest way, using classifying space to look at the higher group. Then it's easier to relate it to the conservation law.
So there's no hierarchy of symmetries here.
There's hierarchy. Actually, this is simple thing. We could have a combination of a zero symmetry and one symmetry. We have a zero symmetry. That means pi1 is non-trivial. But the pi1 can be non-abelian. So zero symmetry can be non-abelian. Pi2, pi3, pi4, and etc. They all are abelian. So that's why this fusion rule of a string and a membrane, they should be abelian to describe by this higher group. So indeed, you are totally right. There's a hierarchy, and those symmetry at different level may twist each other. So they may combine in a different way. And so this really fit very nicely into this kind of some kind, I don't know, this I forgot what's it. There's a classifying manifold using this homotopy group. There's some theory like that. Yeah, that kind of mathematical theory is very useful here.
Thank you.
Maybe we'll just have one more question if there is one, and then we'll break off for tea time.
I have a very lowbrow question. It's just trying to understand right in the beginning where you explained deformations of the Hamiltonian by these local operators.
Yes.
And, the moduli space that you introduced.
Yes.
So by definition of a moduli space, the tangent space at a point is the space of deformations or infinitesimal deformations.
Yes.
So in your moduli space, this tangent space is precisely the space of delta H? Or
yes.
What are these? They're precise.
The delta H is okay, that's a very good question. If you have no symmetry, then delta H can be any local operator. And if you have a symmetry, then delta H will be the symmetric local operators. And also, certainly when you make a large deformation, you may close the gap. So you have to avoid all those neighborhoods where gap closing. So the moduli space is really the deformation which keep a gap finite. All those deformations.
Yeah, no, that and yeah, okay. Also, can you do, so you started with the lattice model, but can you define the same moduli space or play the same game when, for example, if you're looking at the Schrodinger equation on a Riemannian manifold, so your Hamiltonian is the Laplace operator. What would be
yes or no? I'll be worried because the model we considered here have a UV regulation, have UV cutoff, means that if a space have a finite volume, then the total Hilbert space have a finite dimension. So everything is in some sense so-called well-defined.
I see.
And on the continuum manifold, at a high energy, short wavelengths, there's a regulation involved, and there's a concern different regulation may give you different results, and there's a lot of subtlety involved in that. And here we try to avoid that, yeah, by considering lattice system.
Okay. Thank you.
Maybe we'll just take one more question from Juven, and then we'll adjourn for tea time.
Yeah.
Thank you very much. It's really a conceptual question. I feel like there's some conceptual leap. I'm not sure I understand. The question is that Xiao-Gang, you used to emphasize that topological order should not be associated with symmetry because it's robust without symmetry.
Yes.
And a lot of times when you say about like classifying especially invertible anomalies, let's say in D dimension, you associate these anomalies to D+1 dimensional invertible faces. For example, the gauge anomaly in D dimensions, that can be viewed, let's say the Tahoe anomaly with some global symmetry G. Here, the gauge anomaly is a background probe, let's say. They can be understood or classified by D+1 dimensional symmetry protected topological faces, SPD faces. Well, if you have a mixed gauge or gravity anomaly, then if the symmetry is still important, then you still classify that by D+1 dimensional SPD invertible faces. And you also emphasize that if you try to classify D-dimensional gravitational anomaly without the need of any global symmetry, then you try to classify them by D+1D topological order. And then there, for the D-dimensional gravitational anomaly, you don't emphasize global symmetry at all. But here, there's some conceptual difference that you try to associate global symmetry now to a topological order. Can you?
Let me answer your question.
Yeah,
let me using your last point. You know, D-dimensional gravitational anomaly correspond to D+1 dimensional topological order. I'm using this example. Okay. And what is a D-dimensional gravitational anomaly? There's one way to look at this is that the system with the gravitational anomaly means that their total Hilbert space do not have a tensor product decomposition. They cannot be decomposed as a tensor product of a Hilbert space on each site. So this is site-wise tensor product decomposition is not there. Okay, so that's one way to look at the gravitational anomaly. And this kind of abstraction to have a tensor product decomposition, site-wise tensor product decomposition can be viewed as a gravitational anomaly. But however, using this picture, we can associate with the symmetry to gravitational anomaly because when you have a system with a symmetry, you can consider symmetric sub-Hilbert space. The symmetric sub-Hilbert space also do not have a site-wise tensor product decomposition. And so this is another point of view that a symmetry can be described by anomaly or can be described by topological order in one higher dimension. So actually this is the motivation for this picture. It's a symmetric subspace of a symmetric system don't have a site-wise decomposition, the Hilbert space. And that's where actually it's anomaly, the gravitational anomaly. And so the things are, that's how things are connected.
Thank you. I think what we'll do is thank Xiao-Gang again. And
thank you very much. Yeah.
Maybe we'll adjourn for 10 minutes and then reconvene for virtual tea time.
Okay. Is that same Zoom or different Zoom?
Oh, do you not have the link, Lisa? I thought sent you.
I have a Zoom. It's different Zoom, right? I actually log in different Zoom. Okay, I will do that.
Lisa would have sent it to you, and it's a different Zoom link.
Yeah.